Welcome back to G Fun Facts Online. Today, we are going to deconstruct a technological paradox that defines the 21st century. Right now, as humanity trains artificial intelligence models and designs habitation modules for Mars, roughly 2.3 billion people, one-third of our entire species, are still cooking their dinner on the most primitive technology imaginable, an open fire. This isn't just a humanitarian issue, it is a massive engineering failure. The simple act of cooking kills 4 million people every year, which is more than malaria, HIV, and tuberculosis combined. The solution to this crisis isn't just political will. It is rigorous, high-level engineering. We are talking about a radical reimagining of thermodynamics, fluid mechanics, power electronics, and biochemical engineering. Today, we are going deep into the physics of the clean cooking revolution. To build a better solution, we first have to understand exactly why the traditional three-stone fire is such a thermodynamic disaster. When you burn wood or dung in an open fire, you are witnessing a chaotic, inefficient chemical reaction. Ideally, you want complete combustion, where carbon and hydrogen react with oxygen to produce only carbon dioxide and water vapor. But an open fire has terrible air-fuel mixing and low temperatures. This results in incomplete combustion, creating a toxic cocktail of carbon monoxide, methane, and polycyclic aromatic hydrocarbons. The most dangerous byproduct is PM 2.5, particles smaller than 2.5 microns that can enter the bloodstream. A single open fire in a kitchen can generate concentrations of 20,000 micrograms per cubic meter. For context, the World Health Organization safety limit is 15. Furthermore, the thermal efficiency is abysmal, sitting at around 10 to 15%. Most of the energy just radiates away into the atmosphere rather than heating the pot. The engineering mandate, therefore, is to maximize heat transfer efficiency while minimizing particulate emissions. Let's start with the first major leap in engineering: fluid dynamics. For millions of people, biomass is the only fuel available, so engineers had to figure out how to burn it cleanly. This gave us the rocket stove, a concept originally developed by Dr. Larry Winiarski. The rocket stove isn't just a metal bucket, it is a machine that manipulates airflow. The core feature is an L-shaped or J-shaped combustion chamber with a vertical riser. This design exploits the chimney effect. By insulating the vertical riser, the air inside heats up, becomes less dense, and shoots upward. This creates a pressure differential that aggressively pulls fresh, oxygen-rich air into the combustion chamber at the bottom. The insulation is critical here because it creates adiabatic combustion conditions. By keeping the chamber temperature above 600 degrees Celsius, the stove can crack the complex long-chain hydrocarbons found in wood smoke, effectively burning the smoke before it leaves the stove. Another critical feature of the rocket stove is the pot skirt. In an open fire, hot gas flows randomly. In a rocket stove, engineers place a metal skirt around the cooking pot, creating a narrow gap. This maintains a constant cross-sectional area, forcing the hot flue gases to scrape tightly against the sides of the pot. This significantly increases the convective heat transfer coefficient, bumping thermal efficiency up to about 25 to 35%. However, rocket stoves face a challenge known as the turn-down ratio. They are great at boiling water at high power, but they struggle to simmer. Reducing the fuel lowers the temperature, which stops the smoke from burning. Solving this requires variable geometry chambers, a problem modern engineers are still refining. Moving beyond simple combustion, we arrive at the top-lit updraft gasifier, or TLUD. This is where mechanical engineering meets chemical processing. A gasifier doesn't burn wood. It separates the process into two stages: pyrolysis and combustion. In the first stage, biomass is lit from the top, and air from the bottom is restricted. This oxygen-starved environment creates a pyrolysis front that moves downward, decomposing the wood into volatile gases like hydrogen and methane, leaving behind solid biochar. In the second stage, these gases rise to the top where they meet a stream of preheated secondary air. This turbulent mixing zone ignites the gases, creating a clean, blue flame that looks just like a gas stove. The engineering precision here is in the stoichiometric balance. If you have too much primary air, you burn the charcoal. If you have too little secondary air, the smoke escapes unburnt. Advanced gasifiers now use forced draft fans, powered by small thermoelectric generators or batteries, to actively control this air-to-fuel ratio, achieving efficiencies of 50% and cutting particulate matter by 90%. Now, let's transition to the gold standard: electricity. The challenge here is power electronics. Grid instability and low voltage in developing nations make standard appliances useless. This has led to the rise of the electric pressure cooker, or EPC. The EPC solves the energy density problem. By pressurizing the vessel, it raises the boiling point of water to 121 degrees Celsius, cooking beans and grains in half the time. But the real innovation is in the control logic. Engineers have redesigned these units to use a pulse heating algorithm. Instead of drawing continuous power, the heating element switches off once pressure is reached. Heavy insulation retains the heat, and the system only pulses the current briefly to maintain pressure. This allows a family to cook a meal using only 0.3 kilowatt hours, which is low enough to run on a solar home system. For those who prefer frying, engineers are deploying direct DC induction cooktops. Standard induction stoves require AC power, which means if you are on a battery system, you lose energy converting DC to AC through an inverter. New designs use a quasi-resonant inverter topology. They take DC input directly from a battery and use high-frequency switching circuits to drive the induction coil. To maximize efficiency, they utilize zero-voltage switching. This ensures the transistors switch exactly when the voltage across them is zero, minimizing heat stress and boosting efficiency to nearly 95%. These units can even connect directly to solar panels via integrated maximum power point tracking controllers. But what happens when the grid is weak? In many rural villages, long distribution lines create high resistance, leading to voltage drops. If everyone turns on a stove, the grid collapses. The engineering solution is battery buffered cooking. These new stoves have a lithium iron phosphate battery built right into the unit. The stove trickle charges slowly from the weak grid, drawing only 100 watts throughout the day. When it's time to cook, the stove draws high power from its internal battery, not the grid. This is a classic peak shaving technique, stabilizing the grid while giving the user high performance. Let's shift gears to biochemical engineering. For families with livestock, the answer lies in biogas. This turns a waste management problem into an energy solution using an anaerobic digester. This is a sealed tank where methanogenic bacteria break down organic matter in the absence of oxygen. The engineering challenge is optimizing the recipe for these bacteria. The most critical factor is the carbon to nitrogen ratio, which needs to be around 20:1 or 30:1. Too much nitrogen, like pure chicken manure, produces ammonia, which kills the bacteria. Too much carbon, like straw, slows the process down. Engineers also have to manage pH buffering and temperature. Mesophilic bacteria love 35 degrees Celsius. In the high Andes, or the Himalayas, engineers have to design passive solar thermal jackets just to keep the bacteria awake and producing gas. Speaking of solar, let's talk about solar thermal engineering. The flaw with solar cookers is obvious. You can't cook at night. The solution is thermal energy storage using phase change materials, or PCMs. These are substances that absorb massive amounts of latent heat as they melt. Materials like erythritol melt at 118 degrees Celsius, which is perfect for frying. During the day, a solar collector focuses sunlight on a receiver filled with this wax-like material, melting it. In the evening, the user places a pot on the receiver, and as the material re-solidifies, it releases that stored latent heat to cook the food. Because these materials often conduct heat poorly, engineers embed copper fins or graphite matrices into the vessel to extract the heat rapidly when needed. Perhaps the most disruptive innovation isn't in the hardware but in the digital layer. We are seeing the convergence of IoT and carbon finance. High-tech stoves are expensive, so to make them affordable, the industry uses results-based financing. This requires rigorous data. Modern stoves are equipped with K-type thermocouples to measure heat, Hall effect sensors to measure fan speed, and shunt resistors to measure current. Microcontrollers like the 32 Spanish pesetas process this data and transmit it via GSM or LoRaWAN networks. This enables pay-as-you-go models, where a user pays a micropayment via their phone and the stove unlocks for a day. If they stop paying, the stove locks. This de-risks the investment, allowing companies to lease high-tech equipment to low-income users. This data also powers the next generation of carbon credits, known as digital MRV, measurement, reporting, and verification. Instead of guessing how much carbon was saved, algorithms calculate the exact emission reductions in real time based on the sensor data. Some projects are even anchoring this data onto blockchains, like Hedera Hashgraph, creating a digital twin of the stove. This issues a fractional carbon credit token for every specific cooking event, providing total transparency to buyers and financing the deployment of more stoves. Finally, we have to look at the health standards. For years, we distributed improved stoves without knowing if they actually helped. Today, we use the ISO 19867-1 framework. This standard rates stoves from Tier 0 to Tier 5 on efficiency, safety, and emissions. Epidemiological engineering models have shown us that the health curve is non-linear. Reducing smoke by 50% does not reduce pneumonia risk by 50%. You have to get emissions down to near ambient levels, Tier 4 or 5, to see real health gains. This realization has shifted the entire global engineering focus away from slightly better biomass stoves toward truly clean fuels like electricity, gas, and ethanol. Looking to the future, the horizon involves green hydrogen. Institutes like NETRA are testing hydrogen cook stoves, which present a unique challenge because hydrogen has a high flame velocity and low ignition energy, creating a risk of flashback. Engineers are developing catalytic burners using porous media combustion to burn hydrogen flamelessly and safely, producing nothing but water vapor. Furthermore, In the smart village concept, the cooking load becomes an asset to the grid. Smart inverters communicate with a mini-grid controller. If solar generation spikes at noon, the grid signals the stoves to turn on and cook thermal storage meals, effectively using the stove as a battery for the grid. Clean cooking is no longer just about stacking bricks to make a fire. It is a convergence of fluid dynamics, power electronics, biochemistry, and cryptographic security. By treating the humble cookstove as a piece of precision engineering, we are closing in on a solution that can save millions of lives and empower billions of people. Thanks for listening to Fun Facts Online.